bright and early, awake at this early hour. So there is no better way to start off the morning than Chris Ray here. He works on large-scale data management. He's worked on streaming data, probabilistic database, and recently a lot of work in machine learning. And so I'm really looking forward to this talk, and I hope you guys are also.
Thanks, Samir. Thanks a lot. So first, thanks to the organizers for inviting me. It's been a great workshop. Yesterday was fantastic. And thank you all for getting up early in the morning. So as Samir mentioned, I'm actually a database guy, so I have slightly a different take on the big learning kind of thing. And what I'm going to tell you about in the meat of the talk is about my umbrella project, which is this thing Hazy, whose logo is up at the top, which is trying to build and maintain large-scale statistical applications. So not just construct them for one kind of task, but maintain them over time. Okay. Before I get in that, I want to give you some thoughts, though, about, from my perspective, what's interesting about the big data craze or the big learning craze. And I think it's a little bit different than maybe some of the things we've heard so far. So if you haven't heard, big data is the future. Everyone knows this. Even The Economist has this thing that everyone likes to throw up, which is actually the term data deluge, which I think is about 20 years old. But everyone's excited about big data. You know, things like Hadoop have taken off to an unbelievable extent. People are, you know, there's a lot of momentum around it. Everything you want to do, you just do it on Hadoop, and all of a sudden it scales. There's also a bunch of interest from the sort of corporate side. IBM is betting very heavily that Hadoop really is going to be the answer to everything. That's what the Big Insights project is really all about. And even classical database vendors like Greenplum or Oracle, who have had these great relational databases for 30 years, are jumping on the big data train. So big data looks like the future. But being kind of a contrarian, when I look at this, it kind of makes me a little bit uncomfortable, to be honest with you. And the way I think about it is, it's clear to me after thinking about this for a while that big data is absolutely awesome if you're a vendor or you need consulting dollars. If right now you want consulting money, you say, hey, I do big data, someone will give you money. But it's not really clear to me that the big is really the heart of the problem. Okay? So to understand why I don't think it's really the heart of the problem, I want to drill into really what does it mean to be big? Like, what is big data? So how big is big? So is it a gigabyte? Well, it doesn't really intuitively seem all that big, but there have been some, work that you've seen that says, oh, we're doing large-scale stuff. It's a gigabyte. And I'd actually argue that there is interesting stuff in this thing. But it fits on your phone, right? I mean, a gigabyte is not a huge amount of data. It fits on everyone's phone in this room, probably. But yesterday, we heard a talk about embedding processors. And I would argue that the talk of putting convolutions and neural networks inside chips and putting them down there and dealing with gigabyte scale data shares a lot of things with what I find really interesting about big data. So at first, it's suggesting this doesn't really think it's really not that much about the size. So is it a terabyte? Well, a terabyte is big on Hadoop. If you talk to the guys who are in Yahoo, they'll tell you, we have a really large scale machine learning problem. The matrix we're trying to factor, it's about a terabyte. Okay. A terabyte is main memory in a lot of applications. It's not really clear that the terabyte is really where the pain is coming from. Now, I should say my community has a terrible reputation when dealing with people from the Hadoop world. So I do love Hadoop. One of my best friends was the intern who wrote Hadoop. So I'm a booster, okay? So I like this stuff. But it's not that they're dealing with problems that are sort of fundamentally large. It's because they have an infrastructure that is sort of this big data that dealing with a terabyte and dealing with the spills and all that stuff that comes along with it is difficult. So maybe it's a petabyte. Maybe when we get to a petabyte, size is the only important thing. Okay. Now, barring basically two applications that I know about, I don't think you have that problem. One of those is oil. The other one of those we heard yesterday. And even if you saw what happened yesterday in the collider experiments, they very quickly reduced the statistical or the learning problem down to something that was much, much smaller, smaller than any of the order of magnitudes I have up here. So I have here this nice quote from John Doyle, which I like quite a bit, which is, let's end pedophilia. And the thing that he's trying to get across there is just loving size is not a good thing. Okay? It's not about size. So what I'd suggest to you is that something other than size is the common thread on all these different applications that have sort of big data spirit to them. So what is that common thread? What do I think is really interesting? Why do I even not throw up in my mouth a little bit when people say big data? And I do like big data. I'm a booster. So there are big shifts, actually, that are coming, that are driving this big data trend. The first one was an observation that Google gets a lot of credit for, which is that more signal seems to beat more complex model 9 times out of 10. Now clearly this is not a testable statement really in any sense of the word, but the intuition is if you have a hard problem, make sure that you can't solve it by slinging together a bunch of easy data sources that are out there. Very difficult problems can be solved in this way. In fact, this is one of the main drivers why businesses want to acquire big data. Businesses like using simple things like linear models. They understand acquiring a huge amount more data. Say, oh, we need to have more data about our customers. Got it. And then we'll run our linear model. So this is one of the reasons we're really driving. It's one of the driving forces, I would argue. The other thing that's driving this is more at a technical level, and is what ties together, in my mind, the things that we would talk about as a gigabyte scale being in the same spirit as big data. And this sounds at first like a kind of trivial switch, but I think it's actually kind of deep. People are moving now computation to the data, not the other way around. And if you think about it, this is kind of the common theme of the Hadoop stuff, of the stuff that's on an iPhone. It's we're taking a sophisticated computation and putting it to where the data are actually acquired. A terabyte isn't big in Hadoop. I mean, it isn't big in the real world, if you like. And if you could buy main memory for it, you wouldn't do it. But if you're living with an entire processing infrastructure that is Hadoop-based, then you may have to do some of your machine learning inside Hadoop. So looking at all this, this is sort of in the context of this workshop, this is one of the motivations for the kind of work that we're doing in my group. And my bet, looking at these two trends, is really what we need is something that's going to allow us to quickly sling together signals to take advantage of one, where the data live. Okay? So if the data live in a database, we're going to try and push it into a database. If the data lives on your phone, then we're going to try and look on your phone. And as researchers, what we're going to do is try and find the common patterns or the common abstractions that are across each one of these different applications. And that's going to be driving my research group. All right. So that's my thoughts on big data. So now what I'm going to tell you about really, with that little bit of context in mind, is the actual project that I've been pushing on, which is this thing called Hazy. Okay? And Hazy really started when I came to the University of Wisconsin, which was just a couple years ago. And I wanted to, I did some work on probabilistic databases, and I wanted to build real applications. Okay? And probabilistic databases was a great research effort. There were a lot of great theoretical results that came out, but there weren't a lot of real applications that were built. And I wanted to build and understand real applications. And so Hazy really was in response to this. I thought, well, let me look now at the trends that are driving, forward all these different data management issues and try and understand for these kinds of problems, what's really driving them? Why do people care about this messy data, this inconsistent data? And there are two things, I think. The first is now data are available in an unbelievable number of formats. So about the first 30 years of data management, people were really only concerned with traditional record-oriented data, very structured, precise data that looked like banking data. Over the last 10 to 15 years, people have started to look at text because of the advent of the web. But by volume, this is actually a small fraction of the overall amount of data that's available. There's data in video, in speech, in OCR, and in sensor data. And it's not that this data is new per se, but it's that there's real business value in it. So one of my favorite examples is of sensor data. So sensor data has been around for a while, but now people are taking sensors and sticking them on your car and pricing your auto insurance in the US based on it. Flo from Progressive is going to take her little sensor, put it on your car, understand how well you drive, and then charge you based on that information. Okay. A second trend is a continuing trend. It's one I think people in the room are very familiar with, is that there's this continuing arms race to understand your data more deeply. Okay. The reason I use the phrase arms race is that even small changes in how well you understand your data pay off to huge extents. So if you're a scientist and you understand your data slightly better than the other team, then you're the discoverer and they're the also-ran. If you're the business and you come out and you understand the market, that there's an emerging market and no one else does, and you get first mover advantage, you get in there and you take over the market, you're a billion-dollar company and they're nothing. Okay? So there's this huge sort of nonlinearity, if you like, to understanding your data. So for this reason, so looking at these two trends, what I decided to do is say, well, what's the common theme between them? So people in this room definitely know that for the second one, statistical data analysis is, really at the heart of a lot of the state-of-the-art methods. So it makes sense that we're going to have some kind of statistical thing in our background, in our bag of tricks. But actually, in each one of the data acquisition problems above, whether it's OCR or whether it's speech or whether it's the sensor that's in your car, it's first passing through a statistical model before you're actually able to use it in any kind of reasonable applications. So if we want to build something that goes all the way from data acquisition all the way to analysis, we're going to have some amount of statistical tools. So what Hazy is basically taking those statistical tools and integrating them with data management techniques. Now the data management techniques come in right away because if you're pricing someone's insurance, you also have an entire claims infrastructure or reporting infrastructure. You have all those things that live in traditional databases that are being manipulated by an entire tool chain that's 20 years old. So you have to figure out how to put these things together. Now, Hazy's research goal in this context is, as I said, to understand those common patterns. It's not to take every single model in the world and cram it inside whatever system we're looking at and just take every pairwise combination. It's to try and look across the applications that people are actually building and say, here's a common design pattern. The reason that design pattern is so important is that we can abstract it away, and as systems builders say, look, here's a nice decoupling between what you need to do and some operation that's going to have to happen again and again and again. And we can optimize the heck out of it. That's really what systems is all about. Okay. So said more succinctly, the thesis of Hazy is pretty simple. The thesis is the next breakthrough in data analysis may not be a new data analysis algorithm, not an individual particular algorithm that you're adding more fancy tricks to. But I'll bet, and actually I am betting, that it's in the ability to rapidly combine, deploy, and maintain the algorithms that we already have. So what Hazy is going to try and look at is how to take and combine all the different things that are out there. Now, these combinations are going to happen at two levels. There are going to be things that we're going to talk about that are how do we take a big collection of these different tools and sling them together in a nice programming language. That's something we work on in my group. We have a project that I'll show you in a second. There are also other abstractions, and some of the stuff I'll talk about today, which is where we look for common algorithms by which we can implement a whole slew of models. That's the second kind of abstractions that we look for, sort of a common pipe that allows us to implement many, many different machine learning models. And that's what I'll talk about in the technical portion of the talk. Okay. To understand this thesis in any kind of detail, we had to figure out what people were actually doing. Right? What are people doing? So what we did in my group is we started building stuff. Okay? And what I'm going to tell you about are 3 applications that we actually went ahead and built with people who cared about the data to try and understand what they're doing. Now, in each one of these applications, they all have the same flavor. There's something that someone is doing right now in industry, but we're not going to do what they're doing in industry. We're going to do something that's a couple years ahead, or a couple years sort of far out science fiction, since we don't have any competitive advantage on the industrial strength stuff. Okay? So I'll describe both of those parts of the application when I walk through it. So one application that people are doing right now is trying to understand how well products and people are doing in the marketplace. So every company that I'm aware of right now is selling products. They have customer-facing entities. They're running ad campaigns of some sort. And they want to understand certain things about that. How are they being perceived? Now, what's great for them is that never before in history have you been able to get this information more freely. Okay? It's generated on a bunch of different sources right now. It's on Twitter, it's on Facebook, it's on blogs. And what people are doing in a bunch of different startup companies is doing about the simplest thing you can imagine, which is a company comes to you and you figure out a report that says, here's how you're being perceived in New York, or here's how you're being perceived on Twitter. And to a large extent, these reports are constructed manually. Now, a lot of new companies are coming along and they're using tools that you know and love. Right? They're using things like CRFs and support vector machines to extract from all the text that's out there what products are mentioned, what people are mentioned, and how they're being perceived. And they're starting to sling these things together to try and create reports to give to actual companies that care about how they're being perceived. Now, this is a kind of a classical application. This is what people are doing right now. This is not something that we work on in my group. We have no competitive advantage here. What we work on are things like this, which are a little bit farther out. Things like machine reading, which is a big DARPA project. So here, the setup is we're given a huge collection of text, and I'm going to show you this in a little bit of detail. And we're asked questions over that corpus of text, things like, list the members of the Brazilian Olympic team in the corpus with their years of membership. Now, we're not told that we're looking for anything about the Brazilian team ahead of time. We're told things like, you need to know about membership relations. Okay? And moreover, when we answer this question, we have to be able to prove it. So we have to be able to actually return text that says, this particular person was on the team for this length of time. Here's a document that substantiates that, and return reports. Now, you can guess from the fact that DARPA is in front of it, that this is something that would be of interest to the intelligence community. Right? This is basically the intelligence problem. Okay? Read a bunch of text, figure out who's being mentioned, and put them into some kind of organizational hierarchy. So I'm going to walk you through a demo we built that's a little less nefarious in a second. Okay? But first I want to show you how this whole thing works. So the way it works is we have this system which we call Felix. And Felix uses all your favorite characters. Right? It's got Hadoop in there. It's got Greenplum in there. If you know Condor, it's this high throughput workflow system. And Felix is an infrastructure that's talking and stitching together all of these different things. Felix actually, if you're a machine learning, of a certain flavor of machine learning, it's basically a big Markov logic processing infrastructure, which may sound strange that I say that and then stitch together everything. That's what it's doing, though, really. Okay. And what Felix is going to do to answer this thing is going to suck in a huge amount of documents. Now the demo I'm going to show you in a second sucks in about 500 million documents, which is roughly 15 terabytes of data once it's pre-processed and linguistic things. So it's a hefty amount of data. It's not really truly massive, but it's a big amount of data. It's the web. Okay. It also sucks in a bunch of other structured databases, things like Freebase. It's going to suck in all kinds of structured databases that we may write a crawler for. If we're interested in knowing about movies, maybe we'll write a crawler for IMDb and throw that thing in there as well. Okay? And Felix is a very flexible infrastructure to do that. Now, to answer that question that we had on the last slide, we basically do the standard thing that everyone does in text analysis. Okay? And I'm just going to show you this just to introduce some terminology. What we do is we first do a phase called entity linking. We take every document that's out there, and we run every linguistic tool we can imagine on it. Okay, so we run, the NLP tools from Stanford to linguistically parse the entire web. We run all the co-reference tools that are out there. And this gives us basically a very rich feature space for every single mention that we just named entity on the web. People, product, place, thing, capitalized noun, common noun, every noun that we can find. Okay? And we blow up a huge feature vector about it. And then what we try and do is resolve that this particular string is referring to a particular person. Okay? So like this string is actually Barack Obama. Right? It's actually the president and not just some other guy named Barack Obama. That's a phase called entity linking. Once we've done this, we've raised the level of abstraction from text to actual entities that we can reason about and bring into play some of the structured knowledge bases that are on the side. And then we can do something that in the text analysis terminology is called slot filling, which is basically relation extraction, trying to figure out the member of relationships. Now we've figured out all the mentions in the world of the Brazilian Olympic team. We've figured out all the different individuals that are on that team. And now we're going to have to try and pair them up. And what this boils down to, again, is extracting a huge number of features and every signal that we can imagine throwing into this thing to try and figure out that these two are participating in some kind of a relationship. And those features are linguistic cues. Bob was on the team. Okay, that's a pretty good linguistic cue. We'd want to learn that automatically. All right. So, before I show you the demo, and I'm going to show you a very rough demo in a second, I want to explain what the two key features of this system Felix are. The first thing is that Felix is going to allow many of those best-in-breed algorithms to be used for individual points. We're not going to write our own linguistic parser. We're going to use Chris Manning's tool. We're not going to write some little way of doing named entity extraction. We're going to use an off-the-shelf CRF. We're not going to invent a new classification model. We're going to use logistic regression. That's what we're going to use. Okay? So the best-of-breed algorithms for a particular task, we're just going to stitch them together. The second thing, which I'm not going to talk about too much, is that the way we stitch them together is with a very simple rule language. And actually, after I show you the demo, I'll show you that the rules to create the demo are only a couple hundred lines. Okay? And this language looks like SQL, or if it looks like Prolog, or it looks like Datalog, it's a logic-based language. It has some notion of uncertainty in it. It has weights and all kinds of rules. And what this allows us to do is very quickly bring in signals from structured sources with unstructured sources and put them together. It also allows us to give very simple and coarse feedback to the system, like don't do that, okay? Which is very helpful. Here's a rule that you should never violate for consistency. Okay. Now the challenge, and one of the things that's interesting about Felix, is how we scale that up to terabytes, and how we're able to take this very expressive language, this Markov logic language, and run it on the web. But I will, instead of telling you how we do it and all that stuff, I'm just going to show you that we do it. Okay? So just one little bit of sort of pseudo-scientific validation. On the TAC KBP challenge, these text analytics challenge, state-of-the-art systems have an F1 score of about 20. We weren't competing in the challenge. We just spent about 2 weeks, one student, working on this. We were working on a very related challenge, though, called MRKBP for DARPA. But our F1 score was 39. Okay? So we were able to fling these things together, use the best in breed that was out there, and get a very high-quality system, basically out of the box. Okay? All right. So now, awesome animation, and then a quick demo. Here's the awesome animation. All right. We'll have to wait for it to end. Okay, so the demo is admittedly very rough. My student has only been working on this for a couple weeks, but I absolutely love it, and I just like looking at it. So you're going to look at it. All right. Okay, here we go. All right. So this is a web page. This is not public, so hopefully you can't see the URL. But either way, it wouldn't be very hard to reverse engineer what's going on here. What we've done here is we've created a high recall version of Wikipedia. Okay, so we've taken all of Wikipedia. Wikipedia is very high precision, right? It's entered by humans. Every fact that's in there is manually curated and checked. But if you want to know, as I said, every mention of Barack Obama on the web, it can't help you. Okay. Now, what we've done here in the stats thing is you can see from a particular web crawl. It's actually this is a small crawl. This is the clue crawl, not the 50 terabyte crawl. You can see how many times we found Barack Obama mentioned. So he was mentioned here in 210,000 different documents, in 1 million sentences. He was mentioned in some videos metadata. We've only crawled, this only has about 200,000 YouTube videos in it. We should be up in the millions very soon. What's interesting also, and I'll show you in a second, is cute, is that we also find things inside content. So actually in the spoken content, which hopefully we'll be able to pull off, but depends on an internet connection. Okay. So we're constructing this high recall thing. And just to show you that it's more sophisticated than simply text matching, let me read you the second sentence that Felix says. Here's a related entity to Barack Obama, which is Hillary Clinton. Okay, so Hillary Rodham Clinton. So it says, has he forgiven Barack for trouncing good old Hill, otherwise a shoo-in for heading the demo ticket in this election? Okay? It figures out that good old Hill is actually Hillary Rodham Clinton. And if you actually dig through the document provenance, you'll see that it's established who he is, right? And the fact that he is in context with good old Hillary is actually a valuable signal that Bill Clinton being mentioned means that Hillary should also be mentioned. All right. Okay. So we have some high recall stuff. We have some stuff here, and there's some video and content stuff. But I want to show you something else that's pretty cool. Okay. So you've all seen the info box in Wikipedia. Right? So here's Barack Obama's Wikipedia. And what we've done is we've tried to use that relation extraction to substantiate facts that are in that box. So for example, here it says Barack Obama is the President of the United States. That's a fact, right? That he was a President of the United States. And we'd want to substantiate that. Okay. He's a senator from Illinois, so on. Now, unfortunately for font reasons, these won't show up. But what's going on here, if you click on the red icons, it's showing you its sort of top 5 sentences it thinks substantiate this fact. It also, which is not listed, substantiates a whole host of other facts and gives you provenance for those, so you could add them in if you wanted to. You could make a Wikipedia editor on steroids for this, which is one demo project. But what to me is very cool, hopefully we don't have any UI bugs, are things like this. So here we want to know that Barack went to Harvard, okay? That he went to Harvard Law School. And we can substantiate that in a video. Okay. All right, so let's try and figure out how we're going to do this. So here's a video. Wait about 10 seconds, and you'll hear the magic words that Barack went to Harvard Law School, but maybe not in the linguistic order you would expect. Okay. Here, give me 1 second to try and up the volume outside of this business. So we have a little sound issue. Let me pause it. All right. Back out. All right. Now hopefully I have no IMs or anything up so that they will start blasting. All right.
In common too, his mother is from Kenya, just like Barack Obama's father. And his parents, like Barack and Michelle Obama, went to Harvard Law School. But all those things...
So there it had to reason and do actually a little bit of co-ref on the text of the actual video, and it finds the spot in the videos where actually that provenance and relation extraction occurred. Okay? So it's able to do this automatically. There's no hidden tricks here. It's not like my student found this and put it up in there. This right now is all automatic with no human feedback whatsoever. All right. Now, of course, if you were really building a system, and let's say you were taking money for it, you would put in some human feedback, and that's actually where the rules come into play quite a bit, because you can tell it things like don't read different sources. There's all kinds of interesting, crazy sources in here. I shouldn't probably play this, but I get a kick out of it, so I'll do it.
How does it deal with contradictory information?
So what is happening underneath is the language is Markov logic. So what it's doing is every one of these rules is just a fact with a weight on it. Each one of those weights are learned in some way, and it tries to resolve it how best it can. It has some notion of sourcing that allows you to write hard-coded rules to say don't trust particular things. There's actually is a hard-coded rule because I think it's funny to include Fox News videos all the time. So it will try and bias up Fox News videos whenever it can. So here's one of those. So we're trying to establish here that Barack is a United States senator. I probably shouldn't play this, but whatever.
Fortunately, some thought I personally had characterized it inappropriately. I regret that. It was not my intention, and I certainly didn't mean to associate the word terrorist in any way with Senator Obama and his wife. Now,
So that was its finding that actually Barack is a senator. So I was very happy that that was highly rated. My student actually made a different version of the demo where he was automatically learning reliability of sources, and that demo went away, that clip went away, and he fixed that almost instantaneously because I was clicking on that all the time. Okay, so back to it. Okay. So all I want to say about that, okay, we don't have to watch the animation again. All I want to say about the demo is we were able to build it. And because of font reasons, I'm not going to show you the program. If you're interested, I can show you the actual Markov logic that's underneath it that has the weights. That part is public. I can give it to you right away. The reason that the entire site isn't public is I don't trust, well, I shouldn't say it this way. There's a chance that my students may have violated a copyright at some point, so keeping it private is something we'd like to do until we can clear it with everyone that we haven't crawled something inappropriate. Fair enough. Okay, but if you want to see the program and how it actually works, I'm happy to walk you through the infrastructure. All right. Okay, so let's switch gears a little bit. So remember what our goal was. We wanted to understand different applications, and we wanted to understand the common design patterns that occurred across them. So this is a pretty rich application, building this all the way from text all the way to answering questions and building the UI on top. So there are a lot of different pieces there, a lot of different design patterns that you have to abstract out just to be able to build it easily. But let's look at an entirely different domain that has nothing to do with text processing and try and see if we can learn some of these same kind of similar abstractions that are around. So another thing that we work on in my group, and Ben and I collaborate on quite a bit, Ben Recht right up there, is working with a bunch of physicists called IceCube. Okay, and I'm going to describe to you what IceCube is in a second. But basically what's going on here is we have a bunch of physicists, and at a high level, they're going to do some statistical processing to understand and interpolate sensor readings. Right? Remember that this relates kind of to flow sticking that sensor in your car, so there is potentially some downstream business value in it. Okay? Before I tell you specifically what we're doing in this project, let me tell you what IceCube is all about. So IceCube is pretty awesome. As you saw yesterday, physicists are awesome. They get to do crazy things that we need to learn how to lobby as a community. So what these physicists have done over the course of about 20 years is get about $300 million, and they use their $300 million to purchase a gigaton of ice at the South Pole. Okay? It's a couple kilometers deep. Okay? And what they've done to these kilometer cubed block of ice is instrument it with a bunch of sensors. So those little strands there are all hanging sensors about 10 or 20 meters apart. So forget right now. Okay. So each one of the little dots that's shown there is actually these things called a digital optical module. And a digital optical module is about this big around, and what it's doing is it's looking for light basically from the bedrock. Now, at first glance, this seems a little bit strange, right? Why is it looking for light from the bedrock, right? It's ice. Maybe it should be looking at light from the sun. They don't care about light from the sun. They care about very high energy particles, those that can pass through the Earth's crust. And they're basically using the Earth as a gigantic filter, so that when the particle passes through and then interacts inside the ice, they can tell that it has reasonably high energy right off the bat. Okay? Filter out a bunch of false hits. So the way this whole thing works, since it's based at the South Pole, is the following. What happens is a particle goes in, light shoots out, they figure out that there's some kind of detection. The sensors read that there's some light, and I'll show you that in a little bit more detail. They're at the South Pole, though, so an algorithm has to say that this is an interesting event. So to a first approximation, an interesting event is one of these that has passed through the Earth's crust, and not one of these things that's raining in through the top of the ice that is just light scattering around. The reason they have to decide about interesting is they have to ship from the South Pole to Madison. Okay? And they're going to, this satellite link is actually constrained, so they don't want to ship absolutely everything for every one of these events because they're happening, hundreds of times a second, okay, and in very, very small time windows. Once it gets to Madison, there's lots of data analysis that happens, okay, on top of the stack. Now, together with Ben and some students, we're working at both the top level, which is the in Madison, complicated physics detection stuff, but we're also, because these guys are awesome and we really love them, we're also allowed to work at stuff in the pole, okay? And deciding whether or not an event is interesting. So what I'm going to tell you about, just for one slide, is what happens at the pole and what we've been doing with them for the last couple months. So a key step, there are actually a couple, but a key step is basically detecting the track. So what you see on the screen here is basically it's a little bit dim, but you can picture each one of the sensors, and this is the light intensity that's hit the sensors in a particular period of time. This is the data that you get back. The time that each sensor went off, and basically a rough count of the number of photons that actually hit that particular dome. Okay? From that, what we want to do is actually figure out the track of the particle. Now here, this is a pretty good and easy case, right? You can kind of guess that it's through the middle. Now it turns out that the better you can get your angular resolution, the more happier the physicists are. So even with a problem like this, there's some non-trivial amount of engineering that you have to get it perfectly correct. Now, just as another bit, just as an aside, if you look at a lot of the data, there is a lot of noise and spurious stuff inside the data going on all the time. So to decide if something's interesting, as I said, we wanted to figure out if this track is upgoing, right? If it has an upward trend. Now, one thing that's very interesting is the structure that's used actually to do these neutrino calculations. We use very simple stuff. Okay, it shares a lot in common with some of the text processing things that we've done. To cut to the chase, what we actually use are basically simple rules, simple data filtering, and simple regression concatenated together. Okay? It's not a very, very complicated model. Now, you may look at that and say, okay, these guys put some rules together, they did some regression, and the physicists said, hey, that's great, thanks for playing. But actually, even these simple models were able to beat what they had already had on the pole for quite a while. And in fact, Mark Wellens, who's co-advised by Ben and I, his code is going to be pushed to the pole in the next science run. Okay? So what do I take away from this? this paradigm of being able to have simple data filtering, slinging signals together quickly, and using state-of-the-art existing tools. It's like nothing complicated is going on here. It's like Huber laws, just simple, robust regression, concatenated with a bunch of common sense filtering that encodes a little bit of physics knowledge. And we're able to actually improve something that people have worked on for a substantial amount of time. Okay. So I promised you in each one of these applications that there would be a motivation that we care about, and then a callous motivation to make money. So what's the callous motivation to make money here? And yes, I can do it. The point is actually that many of the data analysis that are out there are actually physicists. If you go to Wall Street, culturally, they're really not machine learning people. They're not CS people. They're physicists by and large. They don't know how to program SQL. They don't care really that much about machine learning. They know Monte Carlo. They know a little bit of regression. They have a different bag of tricks than a lot of us have. Now, what was really promising and hopeful to me yesterday during the talk was that we learned that statisticians are there and they're starting to convince some of the younger generation of physicists that yeah, there's real value in these tools and you should learn about them. So it's a really hopeful time for machine learning tools to kind of migrate over there. But historically, the people who are doing this on Wall Street, they don't care two wits about those kind of things. To a first approximation, it's not entirely true. Okay. All right. So the last application will be very brief. The last application is something that my student Arun was doing. And the high-level motivation, the motivation that I care about, the liberal BS motivation, I shouldn't say that. Anyway, is that social scientists have been left out of the digital revolution by and large. Okay? So we've been concentrating a lot on physicists and we help biologists, but social scientists really are still going and looking up books, and I learned that they care about things like what are the other books on the shelf and what books are near it, and they're not being able to search through large volumes of text. Now at Wisconsin, there are a couple of people who are actually trying to change this and trying to look at using computers as a tool to understand their social science better. And one of the things that we looked at, because we were interested in all these different forms of content that are out there, is helping out English professors try and do things like crawling all of their information and doing statistical analysis, just like we would do for the web. The problem and the difference from the web is these guys, all the stuff they care about is in books. And that means that to get at the information, they have to scan them and they have to run OCR on them. Now, you've probably used Google Books, right? You type in something into Google Books, you get the word back, and the word that comes back is correct. Okay? So you're like, oh, OCR works pretty well. That's actually what we thought when we started the project. We weren't interested in doing anything with OCR. But that's because you're sensitive to precision, right? The answers that come back, you appear to be correct. But what about the recall? How many times, if you ask for a word in the corpus, do you actually get it? What fraction of those? Much more difficult question to assess. So when we started doing this, for some of these mining tasks, like finding all the synonyms of a word, we were motivated to try and figure out what are the recall of these tools. And it turns out that the recall is actually quite low. Okay? It's around 30%, at 0.3 if you like. And so that motivates us to go, oh my God, if these people are going to use it for mining, these tools simply aren't appropriate. So I'm not going to hammer too much on the details here, but I'll tell you that basically the underlying model that is used in OCR is actually very similar to the kinds of models that we use in other kinds of labeling tasks, the CRFs. They're called stochastic transducers. But really, if you squint a little bit, they're basically the same kind of CRF-like model that we know and love from machine learning. They grew up with a slightly different tradition, but if you look at the algorithms, if you look at how they're handled, if you look at how to compress them, they're very, very similar. So, you may be surprised, but I can even come up with a callous motivation for doing this. And the callous motivation is that we want to unify these things called content management systems, which are all the rage, if you know about recent acquisitions, with database systems. So if you know what this company, Autonomy, that was acquired by HP for $10 billion, they basically do content management. Okay? Now, content management systems allow you to search your voicemail, your email, stuff like that. What we want to do is integrate them with the rest of the reporting hierarchy inside a database so that you can write reports over your emails and things like that. Okay? Form processing, by the way, turns out to be like a multiple billion-dollar industry that I had absolutely no idea about until I started this. Okay? So there's a bunch of interesting things going on here. So what do I want you to take away from all of these different applications? The first thing is that just taking statistical processing and applying it to a bunch of different domains opens up a huge number of new applications. There's all kinds of fun stuff to do in this space, and there's actually all kinds of low-hanging fruit because there are a huge number of applications that can benefit in some way from being enhanced with noisy data. The goal of what we're doing is to try and develop the ability to rapidly combine, deploy, and maintain all of these existing algorithms. So how are we going to cut down on the effort it requires to go after each one of these models? Now, traditionally, even when I was talking about it in the slides, each one of those models, like a transducer, there's an entire tool chain for how people manipulate transducers. Oh, someone's got an SVM, entire tool chain for that. Oh, logistic regression, that's a different package. That seems ridiculous to me as a systems builder. So what we're going to talk about is a very simple algorithm that allows us to tie many of the underlying problems together. And that algorithm is a simple one. It's an old one, which are incremental gradient methods. And all those things, if you were paying attention that were in bold, those simple models, SVMs, CRFs, all of those things, will fit into a framework that we've implemented in one pipe, so we get all the data management stuff for free, where the data live. Now, we've done this in a couple different places, but I'm going to share two with you if I have time. One is inside a database, which I'll talk about first because it's probably the most alien to you. And then also one that Ben talked about yesterday in the optimization thing we had a poster on, which is doing things in shared memory, which is a paper called Hog Wild, which has a great name. I will try and show you a picture of a pig in a hat no matter what, even if I don't get to it. All right, so where are we in this? So what I showed you is that, we should have 3 application areas for Hazy. What I showed you was the different application areas, and I showed you that there were these common models that were there. This is one low-level way we're going to stitch these things together. As I mentioned offline, if you're interested, I can show you the higher-level way that we stitch these things together, the programming language or Markov logic models. So what we're going to talk about now is a project that's called Victor and its sub-project called Bismarck. We got a student named Victor, so it's a little bit awkward to have a project called Victor too. But now it's called Bismarck by my students. And what this is going to do is it's going to apply those regression kinds of methods inside a parallel database infrastructure. A lot of interesting data lives inside there. And in fact, that web data, even though you think web data must use Hadoop, we only use Hadoop for feature extraction. All the real hardcore processing is done inside a big parallel Greenplum instance, okay? 130 node cluster. So let me show you how that stuff gets done. What I'll do is give you a very simple, very, very quick introduction. I know this is old hat for everyone in the room, but basically the kinds of things that we would want to do are add in things like, this is a little website that was built at Wisconsin's a great website. It's DB Life, built by my colleague. All we want to do is add simple features right now that look like things like classifying publications by subject area. Okay, so we're going to use that as a running example. We have a bunch of papers, and we want to classify them by subject area. And this is some graphical motivation for that. So what we're going to think about are things which are basically linear models. And as everyone here knows, let's take a very simple example where we want to label each paper as a database paper or a non-database paper. So the first thing we're going to do is feature extraction. We're going to take each paper and map it to some high-dimensional space. I got 2 dimensions, so I'll map them to 2 dimensions. Once we have those things, we want to classify them via plane. That's why it's a linear model. Okay, so we want to split them into database papers or not. And the way we're going to do that is try and find that x there, which is the normal vector to the hyperplane. Okay, good enough. All right. So as you know, we're just going to consider a supervised problem for the moment. So our actual input is some set of points is labeled as database papers or not, and we get back to the same model. Okay. So one of the great ideas that I love from optimization is rather than thinking about this algorithmically, we'll think about it in my terms declaratively, and we'll just say that what we're going to do is score each one of those planes. So there are many planes that we could pick, and we're going to pick the one that minimizes some cost function. Okay, so x here is the model, and this is all just a head fake to introduce a bunch of notation without being very dry about it. And we're going to look at things that look like that. Okay, the yi here is a paper vector and its label, so the feature vector and possibly its label as well. Now, the thing that's interesting here is different models, right, give you different f's. So if I want, least squares, I take a square distance. A hinge loss, I get SVM. Log loss, logistic regression. Different f, different model. Throw on a regularizer too if you like. Okay. As a systems person, when you see this as a nice unifying abstraction, when you're told about all these different models, and you say, hey, all of these things are just convex programs, all of a sudden your heart sinks. You say, oh my God, I can implement one thing. I can decouple everything and work on this problem and not have to worry about what people are actually doing and separate the modeling task from the algorithmic task. That is a huge, huge conceptual thing that allows us to do a lot of interesting systems building. It's not ours, obviously. So what we're going to look at are these frameworks of these basically regularized inverse problems. We have a regularizer out in front, or a prior, depending on your terminology. We have a bunch of data points. We're interested in these summable things where we have basically a model and a bunch of different data items. Makes sense in the kinds of applications we care about, that it would have this kind of nice additive structure. Examples of this that we've seen so far, we saw the paper classification fits this model. In neutrino tracking, actually the yi could be the DOM sensor reading. It doesn't have to actually be a label. For the regression problem of the Huber loss, you can crank it in there as well. In CRFs, you have the whole document and the labeling as basically an entire vector. You can cram it, shoehorn it into this model as well, which we were using in the text processing. And in Netflix, you can imagine the y's are the users, movies, and ratings. You all know the Netflix challenge. Okay? So why do I bother introducing all this notation? Well, as I said, conceptually the point is, by looking at this specific problem, we can get a whole slew of applications that we care about. Not absolutely everything, that's not our goal, but a whole slew of interesting applications that we can build, as I'll show you in 1 second, in one simple way. Now, perhaps you won't quite appreciate this because it may seem not very shocking to you, but this technique is no more difficult to compute. All these models are no more difficult to solve than a SQL average, so averaging a bunch of numbers. Okay? That's it. Now, why is that significant? Because database engines are unreal. They are unbelievably fast at aggregating huge sums of numbers, right? Summing up numbers, averaging numbers, and dealing with structures. So as long as we can mimic that data access pattern, we get to leverage 30 years of systems nerds in there, beating the crap out of this thing and making it scale. Okay? So that's going to be the high-level win of tying these things together. Sound good? So what's the technique? So the technique we need is gradient methods. Okay? So gradient methods, we're going to get to incremental in a second, are very simple, right? Just to recall, you start at a point, you compute the gradient, you walk in the opposite direction. Okay? That gives you a nice little equation that looks like this, ignoring step sizes for the moment. Okay? And incremental gradients, right? And as long as it's bowl-shaped or convex, we're going to walk down eventually and get to the bottom, right? It's going to converge. Now, incremental gradient methods, right? The idea is just to select a single data item at once to approximate the gradient. So the same iterative scheme works. Start at an x, approximate the gradient at x, but instead we're going to select some j. You can think about it at random, but that doesn't really matter. Okay? It's easiest to see if it's at random, because clearly it's going to be an unbiased estimate of the gradient. We're going to form some estimate of the gradient. Okay? And then what we're going to do is since we have this estimate of the gradient, we're going to move in the opposite direction with it. Okay. Now, this is a very old classical algorithm. It's known that it converges for convex problems, right? It has known rates of convergence. It's a nice, stable, solid algorithm, okay? That, as Ben has told me, is rediscovered every 10 years. So why do we care about these things? Well, the real, IGMs converge, for many problems, and all those things we care about really are convex. But the real reason we care about them is that they're very, very fast. Okay? They converge very rapidly for the kinds of problems we care about. For messy data kinds of problems, you're going to get something that's very close to the optimal solution. Maybe not 10 to the minus 10 to the optimal solution, but 10 to the minus 2 or 3 very, very quickly. And for the kinds of problems we care about, the noise is so high, that's all we want to get with it. The other reason we care about them is a deep technical connection, okay? Which is that IGM processing is basically isomorphic to the SQL average. Okay? So there's some terminology here that's familiar to database people. The X you can think about as an accumulator. This is just a sum. And G is an expression on a single tuple, okay, which is actually what an aggregation needs. The consequence of this is that we can solve statistical models in a database essentially for free. We can use the infrastructure that's already there. We don't have to do anything else. So if you're not familiar with the way databases work or they aggregate, there are these things that are inside called user-defined aggregations. And they have 3 steps, and it's extremely, extremely simple. There's an initialization thing, which takes a state in. Right? There's a transition, which takes a state and it takes a data item and produces a new state. And then there's a termination state. It's just a little simple automata. Okay? Doesn't care what the functions are as long as it's type 1, as long as it's an automata. Okay? So for average, that state looks like this. This is a naive way to compute average, but it'll suffice for my example. The state is some vector in R2, right? You could say or n cross R2, whatever you want. Number of terms and the running total. The transition function is I take the number of terms I have, the current running total, give a new data item, and add them up. When I'm done, I compute the average. Okay? Not great for numeric precision, but good enough for an example. Now, what's an IGM? The state now gets a fancy name. It's no longer the state. It's now called a model. And that's that X vector. Okay? The transition is I give you a data item, a particular data item. When I read it, I compute the update, and that's my new running count of the model. Exactly the equation, the xk plus 1 xk equation we had on the last slide. When I terminate, it's actually even easier. Hey, I don't need to do anything. I just return the model that I have. Okay? All right, so this is all well and good, and syntactically it's a match. And so we've at least at this point achieved our goal of being able to syntactically shoehorn this stuff into a database. But the question is, does it work? Okay. So there actually are some very subtle differences between what an aggregate assumes and what a gradient is there. But I'm going to argue that they don't matter. So UDAs are typically commutative. They're things where the order of the summation doesn't matter. But gradient methods are commutative, right? If I take the data items in one order versus another order, I may at the end up with a different solution. Okay? They're also algebraic, which doesn't really matter too much here, because it's just a technical thing about how they can be averaged. Okay? So I'm not going to go into that. Now, I'll argue that IGMs, it's not really very hard, are formally neither commutative nor algebraic. So you shouldn't go sticking them into this structure. But they're morally both. Okay? So what do I mean? Well, they're morally commutative in the sense that different orders do give different exact results. But who cares about exact results? We're doing this because we're messing with noisy data anyway. They're converging to the same underlying solution. So it doesn't actually matter which order we evaluate them in. We're eventually going to converge to the same optimal solution. It's a performance thing about how quickly we converge to that solution that the order matters. It's not about correctness. Now, this is the key. Because these two properties which are required for UDAs hold, which basically the system is underlying is assuming is going on, this means that IGMs will work basically in parallel off the shelf. So we can take them and put them into Greenplum and Oracle, which is something that we're doing, and scale them for free. And in fact, all that logistic regression that we were doing on the web in minutes, right, running 16 terabytes through in a couple of minutes, I didn't program all the different ways the data access was going to work. I wasn't intelligently prefetching. I wasn't shuffling the tasks. I wasn't making sure that they were equally balanced on the node. I had to write none of that code. I wrote that stupid, 3-line thing. And actually, my student ended up ripping out my code and putting his in. Okay? So that's it. You write those little gradients, and everything else sings. Okay? And there's a little bit of control software because databases are not ideally suited for iteration. You have to do a little bit of control outside. But that's about it. Now, one thing I wanted to point out while I'm here is an effort called MadLib, which is an open source effort. It'd be great if you guys could contribute to. It's backed by Greenplum, but it's not meant to be tied to Greenplum. They want people to implement algorithms. Now, the reason that this is a little bit unique is because the underlying company, Greenplum, actually will introduce you to customers. They've introduced me to customers. They'll actually tell you about real problems. They're extraordinarily open. So as a plug for them, it's called madlib.net. It's open. It's, I think, Joe Hellerstein's baby from Berkeley. But you should all definitely contribute. So I'll plug them.
So,
sure.
Can I get a few more details about the speed you managed to?
Well, the speed obviously depends on the configuration and the particular problem, right?
Yeah, just give me an example. So, okay, what's a particular problem? How many number of features do you have?
Sure. So let's take the web example. So on the web example, the logistic regression has 46 million features because we throw absolutely everything in it. In that area, this is every linguistic feature, every K-gram.
So are you defining a feature is equivalent to a parameter, or is a feature something else?
No, so for me, a feature is the vector, the yi vector, and there will be a component in the model that's the weight for that feature. So we're doing logistic regression. That's all it's doing.
So for every weight is a parameter. So there's 46 million weights.
Yeah, 46 million weights.
And then how big is the data set you're inputting?
The input data set is 16 terabytes. That's a little bit misleading because there's a lot of compression that goes on essentially under the covers in the system. So it's not that 16 terabytes is necessarily going through the system, but it's on the order of a couple of terabytes.
So the number, what's the number of examples? I'm assuming this is a sparse representation.
Yeah, it's a sparse representation. Yeah, so let me give you some more details about this. So one thing that I glossed over is what we're actually doing here is a technique called distance supervision. So what's going on is that the training examples that we're generating are not hand-generated. It's not as if someone's sitting down and labeling the web. We're using Freebase to basically generate silver standard examples. And what goes on, and the reason I'm hedging a little bit is it's a little bit more complicated. I'm trying to tell this story, but it's a little bit more complicated than that. Under the covers, what happens is a big cross-validation is going on. That the 10 minutes is the whole cross-validation procedure. So you create a bunch of silver standard training examples where you assume that the mappings you have from Wikipedia to ground truth are correct. You learn on that. Get back a loop of the features, you do some cross-validation, a little bit of sparse regression that's bringing down the number of features, a little squash going on. And then what happens is all those features get surfaced back to a human. A human looks, it has a little bit of a ranking thing, and they can select if they want to keep those features or not. That's the real critical loop when I describe the running logistics.
So I'm not worried about the human part of it, or even cross-validation. I'm just worried about the streaming process.
Sure.
So how many examples are there, and how many non-zero features per example?
So the thing is that's a moving target. So I'd be happy to tell you offline the exact number of examples, and actually as soon as we can make the data sets public, I can give you the exact numbers. There are 500 million web pages. I think in the end there are about 80 million mentions. 80 million entities, which each have one of those features in it. The number of non-zeros is recorded somewhere on some web page. I can log in after this talk to try and see if it's recorded on a. We have a wiki where every week we record our progress and what the stats are. I don't remember them, and honestly, my students are running out of front of me. but it's on the order of, as I said, 46 million individual features. The dimension will have a huge number of features because we have all of the linguistic parse information that's around them. So everything that comes back from the parser, all co-reference information. We then blow it up, just as if we're going to go down in detail. The other thing is we then take each one of those mentions and the surrounding mentions. We hit Bing and Google. Bing is giving us a nice little interface. We blow up again those mentions, and then we construct features that are from those mentions. So the way, so in the final analysis, even though it's sparse, the vectors themselves are pretty big. So, you know, they're not, it's not as if we have 46 million features and every mention has like 4 non-zeros. There are a lot of non-zeros there, but I don't remember the exact numbers. I'm happy to, this is stuff that I built, so I'm happy to answer detailed questions all day.
So I just want to get kind of a sense of the throughput of the system.
Yeah, also I should say, the other thing I should mention is every piece of code and data that we're not legally bound not to put on the web, like Barbara says you can't put on the cables between the pipelines, that can go on the web. But almost everything else can go on the web. We put that on the web. We also put up all our code in virtual machines, so it's so easy to download. You just download, click play, you can start playing with it. We also put all our source code on the web, put that in there, and we push our source code into Madlib on our own site. And there's also a GitHub thing. So if you want to try it out, leave it up, tell us what's wrong, we absolutely don't have to do it. So please, definitely, any feedback would be awesome. Okay. Oh, I'm not fine. Yeah, all right. Picture of a Hawaiian hat. I'm going to plug these ones. So, alright, so the students who did the real work in red here, Arun Kumar is the guy who did the staccato project, which is the one that actually was sucking in the OCR data. He's the one who walked around and talked to people. He did an unbelievable job actually figuring out what the real problem is. I wanted to solve a math problem, he wanted to solve a real problem. And then Mark Wells is the guy who talked about who did the trigger software. That doesn't need any plugging. Then my student Levin did a bunch of stuff on maintaining. We didn't talk about maintenance, but it turns out as data arrive, you want to maintain these systems and not redo all the computation from scratch. We have some upcoming papers about this. Aaron Fang did a great job as an IceCube paper coming up. We also have a bunch of stuff about populated knowledge bases from text. There's a preprint up right now, and then there's a DLDB paper about the initial version, which is out of date. New infrastructure. And also Caparella is the guy who did Hadoop. I'm not a Hadoop data. Anyone know Hadoop paper? Look at me. Alright. So what I care to tell you, many statistical data analysis tasks are no more complicated than a SQL average. Certainly not all of them in the world, but a large fraction. We built on this because we wanted to have a single pipe that we could push our analysis as close to where the data live as possible and take advantage of a huge amount of systems engineering we've done over the last 3 decades. I didn't talk about our while, but I did want to plug again. Code data papers. Everything we have has to go on the web, otherwise it's students hide from me. So it's all in there. List.edu/hazy, and also linked off my homepage as the current projects. Everything's on there. You find a bug, you find something you don't like, you beat us up, we're very happy. We don't care when people beat us, but we're very happy about it actually, because that means someone used our stuff. All right, thank you so much.
So we have time for a few questions while Joey said it.
So, you know, the idea of trying to take machine learning algorithms and implement them on top of some of the great infrastructure that's been built by database people is appealing. But I think there's also the danger that if the database is trying to solve a more general problem, so this might happen with some of these incremental gradient methods, then maybe you're paying some additional overhead because it has to be able to deal with cases that you don't need.
Right, so that's a great point. So there are 2 ways you can go with this, right? So you can take, you have 2 options. You can take incremental gradient methods and you can build your own system from scratch, and there are great systems that are doing that. That's definitely a very plausible way to proceed. There's a second approach which says, look, there's an entire tooling infrastructure that's there, and maybe we're going to run 10% slower than we could if we absolutely optimally tuned everything for incremental gradients. But we're going to be running on data that people care about right now and want to have those tools in their tool chain. So we're willing to make that trade-off. Now down the road, what seems to already be happening, especially with these guys like Greenplum who are very open, is that you say, hey, your page format is killing us. You're costing us, a factor of 2 because of the weird way you do a copy. They're actually very responsive to trying to fix and do those things because there's enough money behind it that being 2x faster is something they can go to a competitor and say, hey, we're 2x faster than Oracle, you should buy our product. So as long as there's competitive pressure, some of those engineering details of getting rid of the overheads will be there. Now, I actually think it's pretty ideal infrastructure to implement specifically incremental gradient methods because they're just stochastic atomic. That's all they're really doing. So that is what a UDA is doing. So I'm not sure that there's a fundamental reason roadblock we're going to run into, but it'd be exciting to find out.
So if we can manage to pin down the throughput you're getting, I think we can get a good understanding of overhead. Your heads up.
Let's do that one. Sorry. It's a good discussion. We need to get slides. So all the slides, we just come up and try to do this quickly.